Valerie, what? Oh, you wrote a new one? Oh, I just saw this one too. Oh, okay, so Valerie has written another one for me, and I guess we're looking at imaginary poles and stability. So we'll do that. Okay, so we have the transfer function again. What we'd like to do is factor it, like we did last time when we had the real poles. But we see when we try to factor this, this does not factor very nicely. So we can't use our traditional method of just factoring and just picking the values easily. We have to do something a little bit slightly more complicated, but still very easy. So, well, first let's do the easier part. Let's find the zeros for this system. So our 0 here would be -1, because that s of -1 makes this numerator 0. So now let's try to find the poles. All right, so we can't factor this directly, so we have to use the quadratic formula. So for that, we have to find s equal the opposite of b, so -2 plus or minus the square root of b squared minus 4a, which is 1, and c, which is 2. All of that over 2 times a. So there's our setup, and now we just need to solve for this. So we see that if we, well, do one thing at a time, -2 plus or minus something all over 2. So now we have to solve inside the radical. So we have to do 4 minus 8, so that's a -4. And if we solve this out, we'll see that we get a -1 plus or minus. We have a negative under the radical, so we bring out j, and then we just have 2 over 2, so we get 1. So these would be our poles. And here is our 0. So first, let's bring it over to our nicely drawn real and imaginary axis for the pole 0 diagram. And we see that the 0 is at -1, so we put our little 0 here. And then we have our our poles at -1 plus or minus j. So we have one here and here. And often these will come in pairs, so they'll be often mirrored across the real axis. And that's the case here. So we have two poles, and they are in, well, this side we call the left half plane. And the right half plane would be this side, so the right side of the imaginary axis. And we see that our two poles are in the left half plane, and we know that they will then be stable. So now I'm going to show you a little bit of why this system will be stable. All right, so we know our poles and zeros, and let's try to think back to what this means in the time domain. So we look at this, we can't factor the denominator, so we can't break it apart like we did last time. So we have to actually think about this in terms of cosine and sines. So if we look up in a table, we will see that if we know a transfer function that looks like this, so s plus alpha and then s plus alpha in the denominator squared plus an omega here, we can take the inverse Laplace of this, and we will get an expression e negative alpha t times cosine of omega t times u of t, where this is our unit step. If, again, we assume that we have 0 initial conditions, such that we start at 0, so we can kind of just ignore this unit step notation, then we would get e to the negative alpha t cosine of omega t. And this is essentially a decaying exponential with some oscillation multiplied by it. And this will be a stable system. So if we can map this to look like that, take the inverse transfer function, inverse Laplace, and make it look like this, then we can analyze it. So let's try to put this in that form. Okay, well, let's first just try to equate them and see what happens. So if we take this, s squared plus 2s plus 2, and we want to make it look like this, so let's just start with s plus alpha. And we'll take this and we'll actually multiply this out. So we'll do s squared plus 2 alpha s plus, and square the alpha, alpha squared plus omega squared. We will see that we get some equating values here. So from the top we can see that alpha should be equal to to 1. Alpha should be equal to 1. And then these match up very nicely. So alpha 1 here matches here. So now we just need 2 to equal alpha squared plus omega squared. We already know that alpha squared is 1, so we get 2 equals 1 plus omega squared. So if we let omega be equal to 1, then this is satisfied. So we have these two values, and now we can transform our transfer function into the time domain. So if we take down here, take the inverse Laplace, and we assume 0 initial conditions, then we can write this as this expression. So f of t will be equal to e to the negative alpha, which is 1, so just negative t, times cosine of omega, which is 1, so just t. And if we look at what this looks like on a graph in the time domain, then we will get, so it starts out about 1, and it will, the exponential part will decay right towards 0. And actually we need to kind of mirror this on the negative part too. What our actual function will look like is that exponent times the cosine. So it'll start up here and it'll oscillate back and forth. But as time goes to infinity, our system will also go to, well, it will go to 0. So as t goes to infinity, our system goes to 0, and we know that that is stable. Hooray! So from this example, we can see that we had poles in the left half plane. They're imaginary, but we were able to transform it into an exponential times a cosine, so some oscillatory component. I'll caveat this with the fact that I chose a very nice system to put us directly into this form, but if you have any system with imaginary poles, you can put it into this form or a combination of cosine and sines, and then you can do the same process and go into an exponential decay times some sort of oscillating function. So short story is, if you can find the poles and they're all in the left half plane, then you can say that the system is stable. And we'll be using that in the future to analyze our system. So hope that helped. So we're back for a clarification. And after some questions from students that I had today, I realized that there was some confusion point, and it's because I misspoke a little bit, and I want to just clarify what we're talking about here. So the thing I'm talking about here is when I said 0 initial conditions, I don't actually mean 0 initial conditions for the function, because clearly I've drawn this with not 0 initial conditions. What I actually mean to say is that, I'm going to erase this stuff. What I actually mean to say is that we have 0 initial conditions as we approach 0 from the negative side. So 0 initial conditions from, I guess, from negative. And what this really means is that we're looking at how the system reacts to a step function. So if this is the time domain, we're really looking at u of t. And u of t is just a step function here. We're essentially hitting the system with a step, so we're changing it. But before, as we approach time equals 0, from the negative side, we're 0. And that's what I meant to say when I said 0 initial conditions, from the negative side approaching 0. So just wanted to clarify that what we're really doing here is just seeing how the system reacts when a step function hits a system. So I hope that clears up the confusion. It just so that when we take the Laplace transform, we don't get our extra, we can kind of make this equal to 1 and get rid of our any conditions that rely on the negative side going to 0. So I hope that's clearer. The process is still the same. I just wanted to make sure you understand why that happens.